So let us see what are the three axioms of probability here. So axiom 1, so which is the probability of an event which always lies between 0 and 1, and the axiom 2 which says the probability of the entire sample space must be equal to 1, and A3, if you have mutually exclusive events like E1, E2, E3 and all, you assume that these are mutually exclusive, then the probability of union of these EIs, they may be finite or infinite. For any of them it is true. So this is going to be summation probability of EIs. You can write it for an infinite case and so on. So this I you can run it from 1 to infinite. So these are the three axioms of probability, and the definition we have taken here is you are performing a random experiment for which you know what is the sample space, and now you are defining a function from uh, a function on the sample space. Like you are taking all subsets of the sample space. Those are what we call events. For each event you are assigning a number. Of course, a number which lies in between 0 and 1, or either 0 or 1. And that function has to satisfy these three properties or these three axioms, which are probability of E always lies between 0 and 1, and P of S is equal to 1. And for mutually exclusive sets, this is what should happen, right? Now I gave you an exercise yesterday. What is that exercise? At the end, I gave you three questions. Do you remember? Of course, I think in the middle also I gave you one question. Number of elements in A union B complement. So first let me talk about it, and later I'll come to that. So this is the part, right, I gave you yesterday. Let me cut it here. So these are the three questions I gave you yesterday. So the probability of E complement. You need to find it using these three axioms of the probability only. Okay, you're not allowed to use the normal definition, like whatever you have seen earlier. So the earlier definition is this, like number of elements in that event divided by number of elements in the sample space. You can take the definition when you know that the sample space has outcomes which are equally likely. Then only you can use the definition, not every time. Okay. So let me prove the first one. So the first one is probability of E complement. What is it? We'd like to know, of course, and we'd like to prove this is nothing but 1 minus P of E. Okay. Let's prove it. You know the entire sample space can be expressed as U E union E complement, isn't it? So I'm just writing the entire set S in terms of E and its complement. If you take E and its complement union, then definitely you get S only. And we know one thing. We know that E intersection E complement is empty. Empty, it means that E and E complement are mutually exclusive. So once if they are mutually exclusive, using the third axiom of the probability, I can say that so the probability of E union E complement, that can be expressed as P of E plus P of E complement using the third example. And you know this is nothing but S, the entire sample space. So P of S, that is equal to P of E plus P of E complement. Now from this you can see what is probability of the E complement. You know the P of S is 1 from the second exam. So let me take one more step. So therefore we can conclude that the probability of E complement is nothing but 1 minus P of E. See here actually we have taken a new definition. So in that new definition we are showing that everything works. That's what we are actually doing here. Okay. So probability of E complement I can take it as 1 minus P of E. Next. And the next one. If E is contained in F, we need to show the chance of getting E is always less than or equal to the chance of getting F. Okay. Has anybody tried this proof? Hello? Have you tried it? No replies. Okay. See here you have two sets. One is F, and in which you know E is contained in. This is E, and these two sets are contained in the sample space. You have a big set that is the sample space. Now here I'd like to express this F in terms of E, that is happening of E and non-happening of E. Okay. I'd like to write F as E union. It means when E happens, or the elements in E, union with the elements in F which are not in E. How do you take that set? Means you need to write these elements in F which are not in E. Yeah, you can take F minus E, but I don't like to use that minus right now. I'd like to use intersection. Can you tell me in terms of intersection? Can you see that region as yeah. What is your answer? Yes, intersection F. That gives me entire F. E complement intersection F. Very good. Or let me write it as F intersection with E complement. So this is the region exactly F intersection with E complement. See, E complement is are the elements which are outside the E, right? So you're going to get all these elements, but I want the elements in F and in E complement. So these are the elements. So that is F intersection E complement. And one thing I'd like to mention here. So I'm going to write A intersection B as AB here. Okay, this is just my notation. I'm not saying that this is a product. Whenever you see in this course, you take it as A intersection B. Okay. Now let us try to see what is the probability of f. See, can you tell me one thing? This E and F intersection E complement, are they mutually exclusive? What can you say about E intersection with F intersection with E complement? F intersection with E complement, that is one set, and that intersection with E, what is that set? That is going to be empty set, right? So these two sets are mutually disjoint. Since they are disjoint, I can write their probability as sum. So this is P of E union F intersection with E complement. So since they are disjoint, I can simply write them as P of E plus the probability of F into E complement, intersection with E complement. Now you see the chance of happening of F is equal to the chance of happening of E plus extra. From this, can I directly conclude that probability of F, I mean P of F, it should be greater than or equal to P of E? Let me write this inequality here so that I can keep it. See, P of an event, that is always lies between 0 and 1. It means it is a positive number. So for P of E, you're adding a positive number, so then the result will be either equal to P of E or more than that. When it is 0, it is equal to P of E. If it is not 0, that is more than P of E. So definitely I can say that probability of F is greater than or equal to P of E from this, right? Since let me write it here. 0 less than or equal to probability of any event, not only for this, E complement is less than or equal to 1. Okay, so this is the result we'd like to prove. I used only axiom of the third axiom of the probability here, nothing else. I have written that set, the big set, as union of two mutually disjoint sets. And then I have seen their probabilities and I got the result. Okay? Yes. E is contained enough. Contained in C. I have written this subset and as well as equal to symbol here. That may be a subset or it may be equal to F. Here, okay. Then I need to make a small change here. Let me remove this. If I keep E is contained in, like if I keep equal to symbol here, then you can keep it here. If it is a strict inequality here, then definitely here also you'll get a strict inequality. Yeah, that's why while proving I changed it here. I wrote equal to. Okay. And of course you can prove that if it is strict, you can prove this is also strict inequality. Why? Because uh, E F intersection with E complement, definitely that is not going to be 0 because F intersection with E complement is not an empty set. If it is an empty set, then we know its probability is 0. Of course, the probability is 0 implies that that is an empty set. It is an impossible event. Okay, if you have equal to here, then you'll get an equal to here. That's it. And let me write that. So the probability of F will be equal to the probability of E when E is equal to F. Next, we have one more exam. What is it? Prove that P of E union F equal to this. Okay. Third one. So now you have two events of a sample space E and F. Now you need to show that probability of their union is equal to this. Yeah. So how do you do it? First of all, let me take two things here, like E and F. Now I want to see the probability of E union F. See, can I write it like this? E union F, can it be expressed as E union, like this entire the entire set I am seeing the happening or non-happening of E. So that is what I am writing it as E union with. See, I want to write this as a union of two mutually exclusive sets. I want to write this entire set as a union of two mutually exclusive sets. So the one chance is this. You can see this one as a single set, okay, and you can see the other one as another set. Now you see that these two sets are disjoint and their union is nothing but E union F only. Now can you tell me how to write this guy? See, here you are taking the entire F. You are taking entire F. So you can write this as F union with. Now I need to represent only this part. It means the elements in E which are not in F. Elements in E which are not in F. We can write it like this here. E intersection with F complement. Because you want to remove the elements in the F, right? So you just take F complement and you intersect with E. So you'll exactly get this part. E, elements in E which are not in F. Okay, E intersection with F complement will do that. But here I'd like to write in terms of E, but this also you can take, no issues. Or let me take this one only. So this can be expressed as F union with E intersection with F complement. So we have written this union as a union of two mutually disjoint sets. So mutually exclusive sets. So now let me look at their union. And before that, let me tell you one thing. Here, F intersection with E of F complement, that is equal to empty set. There is nothing in their intersection. Now you can use our third axiom of the probability. So this probability is same as P of F of union with E intersection with F complement. Since these two are disjoint, I can express this as probability of F plus the probability of E intersection with F complement. Okay, so this is what I get. So the probability of E union F. Let me take as equation expression 1. Next, now we have a trouble here. We have E intersection with complement. But what is it we are expecting here? We are expecting P of E minus P of E intersection F. Okay. So now let us try to express this E in terms of F. I mean, can you express E in terms of happening or non-happening of F? Let me draw a picture. I have E here, right? So now I want to write this E in terms of happening or non-happening of F. So if F happens, then this is where E happens. If F doesn't happen, then this is where E happens. So you can see E as union of two disjoint sets. So this is nothing but exactly E intersection with F. So one part is E intersection with F, right? And the other part union. So I need to write the red color part, and which is nothing but intersection with F complement. Okay, and you can see that these two are disjoint. Now therefore, I can say the probability of this event E can be expressed as probability of E intersection F, right? Okay, I'll write one more step. Union with E intersection F complement. Since those two are disjoint, I can write here E intersection F plus P of E intersection with F complement. This is what P of E. Now what I need here is E intersection F complement. So let me keep it one side and bring everything other side. So this implies I can say that so the probability of E intersection with F complement, that is nothing but P of E minus P of E intersection with F. This is what we got. Now let equation. The first equation we obtained is this. The probability of E union F, that's equal to probability of F minus, I think we got less, right? So the probability of E intersection with F complement. This is what exactly P of E plus, I think I wrote wrong. This must be F. This must be F. So this is P of E minus P of E intersection F. Therefore we proved the result. So we can see that the probability of E union F, this is same as the probability of E plus the probability of F minus the probability of E intersection F. So using this
Okay, so let's look at a case here. So if a coin is there and a head were twice as likely to appear as a tail, then we would have. So what is the probability of getting here? The probability of getting it here. So this is what I'd like to know. Okay. Now here, so one thing I know, my experiment will be tossing a coin. Okay, if you toss a coin, how many you're going to get? You're going to have only two outcomes. The two outcomes are either it is going to be head or it is going to be tail. So now your sample space has only two elements, and you know one. The probability of S must be equal to 1 from the second axiom of probability, right? And you know that this S can be union of singleton events. Of course, you can express this as union of two disjoint events. So one thing I know, the P of S must be equal to probability of getting head plus the probability of getting tail. Since these two are mutually disjoint from the third axiom, I can directly write. And some information is given here. What is that? A coin is unbiased and head were twice as likely to appear as a tail. It means if tail appeared for let's say three times when you toss uh, a coin for three times, now the chance of getting head there is going to be 6. See here, one thing I know, the chance of getting head is twice as likely as tail. This is what it is. This is what the information they have. Right now, using this, they'd like to conclude what is the probability of H and the probability of tail. So okay, here we have an easily tell. So we know this must be 1, and here I'll have in place of P of H, what is it? I'll have 2 times of P of T. So that is 2 times of P of T plus P of T. So from this, I can see that times of P of T must be equal to 1. I'm going up, so the probability of getting tail is nothing but 1 by 3. So if the probability of getting tail is 1 by 3, what is the probability of getting head? So the probability of getting head is 2. Yeah, this is how I should say earlier. I think I told it in the wrong way. If you toss a coin for 3 times, if you know that 1 time tail occurred, it should happen that 2 times head should occur. The chance of getting head is more than chance of getting tail. So this is how you can see the probabilities. And here, if you take a biased coin, you can clearly see that the outcomes are not equally likely. And this axiomatic definition is very helpful while defining these uh, probabilities where the sample space do not have equally likely outcomes. Okay. Next, let us do one thing. Let us look at a definition sample space have equally likely outcomes. And not only just equally likely outcomes, this is only the definition what I'm going to give now, that is only applicable for finite sets, not for an infinite set. See, you can have a random experiment which may have infinitely many outcomes. What is a random experiment? Can you give me an example of a random experiment in which you can have infinitely many outcomes? Yeah, 2 by 3, 1 by 3, good. Okay, think about it. A random experiment which has infinitely many outcomes. You think about all possibility. Experiment which has countably many outcomes, finitely many outcomes, infinitely many outcomes, and uncountably many outcomes. So here, I am taking a random experiment which has finitely many outcomes. Okay. So this is what I'm going to discuss about sample space. This board is not working properly. So let me type it instead of writing. You try to consider a random experiment. Whose sample space is finite. Okay, and say that S is equal to I think I can write it here 1 comma 2 comma 3 and so on and so on n. Okay. And here we are assuming that all outcomes are equally likely. No need to write all outcomes. Outcomes are equally likely. It means we can say the chance of getting 1 that is same as this is capital N and 2 and 3 here. And from the axioms of probability only we are going to take this definition. Okay. So you know all these events are mutually exclusive. The all elementary events are mutually exclusive, right? And also they are exhaustive. You can observe that.
So they are mutually exclusive and exhaustive. Then you can simply say that, or let me write it from now. So the probability of the singleton 1, right? Uh, the probability of the singleton 2 plus and so on, plus the probability of the singleton n, that is equal to 1, because the union is equal to the sample space, and they are mutually exclusive, so their union, you can write it as sum here. So since all are equal to the same number, you can replace everything with p of I itself. Okay, there are n numbers, so n times of p of I, that is equal to 1. So from this E, the probability of getting this elementary event is nothing but 1 by n, right? And this is true for every I. Okay, define what is an probability of an event. Now let me consider an event here. Let the event E here is I1, I2, and so on. Let's assume that there are R elements in this event. Okay. Now you can actually write this entire union of singletons. It is union of Ik, where k is running from 1 to R. Okay. Now you know that these singletons are anyway, they are disjoint, right? So now I'd like to of getting